All right, let's dive right into this explainer. If you've ever find yourself staring at a glowing screen of statistical output, wondering if your findings are actually legit, well, you're in the right place. Today, we're focusing entirely on the assumption check for regression. We're going to walk through the absolutely crucial, but honestly often overlooked, pre-flight checklist for multiple regression.
So what actually happens if your data lies? Or, more accurately, what if it subtly breaks the underlying mathematical rules of the tests you're trying to run? Before anyone can publish those fascinating headline-grabbing findings, we have to make sure our data isn't secretly crashing the model behind the scenes. Because if you break these core statistical rules, your software, it doesn't care. It'll still spit out an answer for sure, but that answer might be literal nonsense. To really get a feel for the stakes here, think about a recent study on Roman heritage consumption. The researchers had a really cool question. Does a tourist's place attachment, their emotional connection to a location, combined with their event involvement, actually drive their intention to revisit Rome? It's a fantastic premise. But before they could confidently declare that place attachment drives revisit intentions, they had to mathematically validate that data first. They had to run a rigorous assumption check for regression, just to prove the model wasn't built on sand.
So, here's our agenda. This is the step-by-step diagnostic journey we'll take to give our data its final clearance. We'll hit why we check these assumptions, run through pre-analysis and data screening, tackle linearity and homoscedasticity, look at multicollinearity and independent errors, and wrap up with the normality of residuals. Let's get into it. Section 1. Why check regression assumptions, or the stakes of data validation? Let's talk about why we actually bother running these diagnostic checks in the first place. Now, this diagram is basically our master roadmap. Think of it as a giant visual spider diagram summarizing the entire pre-flight checklist. Notice how it's broken down? We've got pre-analysis outside of SPSS, data screening inside SPSS, descriptive checks, and finally, the actual model checks themselves. It's a sequence, right? You can't just skip ahead to step 4. You gotta follow the path to make sure the integrity of your regression analysis is rock solid. Section 2, pre-analysis and data screening. This is where we go hunting for outliers. We need to screen our sample size and really dig into the data for those extreme multivariate outliers that could just completely distort the whole model. And to do that, enter the Mahalanobis distance score. When you run your data screening, your software calculates this distance for every single case. The big takeaway here is that if you're running a study with 3 dependent variables, a Mahalanobis distance score over 16.27, that flags a severe multivariate outlier. If a participant hits that critical value, they are behaving so wildly differently from everyone else that their single data point could completely skew your entire regression. Now look at how the critical value for evaluating these distances scales up as you add more dependent variables. It's a sliding scale. If you only have 2 dependent variables, your critical threshold is a tight 13.82. But if you're dealing with a complex setup, say 5 dependent variables, well, the data just naturally has more room to vary before it's considered extreme. So the critical value jumps up to 20.52. If you spot extreme cases blowing past these numbers, you really have to consider deleting them and saving a fresh, clean dataset. Section 3, linearity and homoscedasticity, where we diagnose the model's shape. This brings us to the big 4 assumptions of the regression model itself. First up, linearity. We have to make sure our variables are actually related in a straight line fashion, not some weird curve. We verify this by generating a matrix of scatter plots. The core assumption here is that as your independent variables go up, the dependent variable either steadily rises or steadily falls. If you pull up a scatter plot and see a massive U-shape or a dramatic curve, yeah, a standard linear regression just isn't going to cut it. Next is homoscedasticity. It's a big word, but it just means the variance of our residual stays beautifully consistent across all the predictor levels. Basically, the errors in your prediction shouldn't suddenly get massively larger or smaller as you move along the graph. The spread of those data points needs to remain relatively uniform. So when you're eyeballing your scatter plots, you are desperately hoping to see an even cigar-shaped spread. That nice, horizontal, roughly rectangular band means your errors are consistent. You've officially met the assumption of homoscedasticity. But if you see a cone shape, red alert. Your model is failing the assumption. It's suffering from heteroscedasticity. That basically means your model predicts things really well at one end of the graph, but completely falls apart and fans out at the other. Moving on to Section 4, multicollinearity and independent errors. This part is all about avoiding data overlaps, making sure our variables, or our subjects, aren't stepping on each other's toes and ruining the math. So multicollinearity. This happens when variables are so highly correlated that one is basically just a clone of the other. Imagine if ice cream consumption and chocolate consumption predicted test grades so similarly that you could swap them and the equation wouldn't even flinch. If two independent variables are highly correlated like that, they're essentially fighting for the exact same explanatory power in your model, and that will totally scramble your regression coefficients. A quick way to spot this: check your correlation matrix. If you see a relationship hanging out up around 0.8 or 0.9, that is a massive red flag for multicollinearity. It means those two predictor variables are acting almost identically in your dataset. Alternatively, you can look at the variance inflation factor, or VIF, in your output. It's pretty simple. A VIF under 10, you're good to go. But if it's over 10, you've got a definitive multicollinearity problem on your hands that you have to fix before you can trust the model. Within this same step, we also have to confirm independent errors, meaning one subject's data shouldn't unfairly influence another's. Let's say you're studying students in nested study groups. Their study habits are probably way more similar to their group mates than to total strangers, right? That completely violates independence. To check this, we look at the Durbin-Watson statistic. You want that number sitting safely in the sweet spot between 1 and 3. Okay, but what if things go wrong? If any of these assumptions fail, here's how you clear the error. If you've got multicollinearity, you can try combining variables, transforming them, or just carefully dropping the misbehaving data. Honestly, just removing one of the highly correlated variables from the pair is usually the cleanest, fastest way to save your multiple regression model. Which brings us to Section 5, the normality of residuals. This is our final clearance check. For this, you just generate a histogram with a normal curve superimposed on top. We're verifying that the errors in the model's estimation follow a classic symmetrical bell curve distribution. You want the bulk of your errors clumping right around 0 in the middle and then tapering off nicely on the high and low ends. Usually, just eyeballing this normal PP plot or histogram is plenty to verify this final assumption. And that brings us full circle right back to our master checklist. Think about it. If your data passes the outlier screening, proves it has linearity, maintains homoscedasticity, avoids multicollinearity, ensures independent errors, and shows normality of residuals, wow, congratulations! Your regression model is statistically cleared for takeoff. Now you can actually confidently interpret your findings. Which leaves us with this final, kind of unsettling thought. If a researcher ignores just one of these subtle diagnostic warnings, like, say, a cone-shaped scatterplot screaming heteroscedasticity, how many published breakthroughs out there in the world are actually just mathematical illusions? It really makes you appreciate the rigorous, behind-the-scenes groundwork required to produce true, reliable data. Thanks for joining me on this explainer, and remember, always question the data.